Welcome, this is the fourth final installment of the astronomy videos. We're looking at supernova, neutron stars and black holes, and we're going to be looking at a lot of good stuff, how they work, how they evolve, what the final sort of fate of them are, and how black holes are formed, and this idea of the event horizon, which is obviously a great topic for science fiction movies. So what is the defining features of these things? Well, they all come from big stars. Okay, bigger stars have got greater force, greater gravitational force, crushing that core, and as a result of that, they can fuse the material in the core much quicker, and so they live for literally a thousandth of the time that smaller stars would live. As you know, you may remember from an earlier video, some of the smaller M-class stars on the main scale are just burning their first incantation. You know, they're formed not long after the Big Bang, and they're still burning today. Now, as you know, this pressure of the gravity crushing down the core allows temperatures to rise and fusion to take place. Big stars, okay, can go on fusing beyond the idea of fusing helium into oxygen and carbon. They can then fuse these oxygen and carbon into all the way, as you can see from this element, they can fuse to carbon and oxygen all the way up to iron 56, and that's the furthest you can go with a in the fusion of a star. Okay, in terms of getting energy out due to fusion. Anything bigger than this gets made during a supernova explosion, and that is basically the end result for these bigger stars. So what happens is when they finally when the core gets turned to iron, there's no more fusion that can take place, and basically the same thing happens with our sun. There's fusion stops and everything falls down. All the radiation pressure that's blowing out these layers of the star suddenly stops, and as a result, gravity just causes everything to fall in. Now what happens, it gets so dense that basically the electrons are pushed onto protons and we form neutrons. Okay, and we end up basically creating this super solid core of sort of pure neutrons. Okay, now as everything falls in, it can't be crushed anymore, and it just simply bounces off. You get this shock wave, everything bouncing off and bouncing back out on it, and it's called a supernova. And they are spectacularly bright. Okay, they typically outshine the entire galaxy that they are in. Okay, so to put it in context, the brilliance or the luminosity of a supernova explosion is typically 10 to the 9 times the luminosity of our sun. Okay, so that's like 1,000 million times as bright as our sun. It literally will outshine its entire galaxy. So these are the different types of supernova that we get. Now, when you look at them, we only really need to concern ourselves with the fact that they are all have these key things, the lines in the spectrum. Okay, and the one that we're interested in mostly is the type 1a supernova. Now, what happens with the type 1a supernova, we think, is this. First thing to understand is that many stars in the galaxy, in the universe, are formed in binaries. Okay, and that means that they are going around each other in pairs. And we think that what happens with the type 1a supernova is that a white dwarf, an existing white dwarf, attracts matter from its binary star that it's going around, and then it basically gets to the Chandra limit, which is the limit it can get to, and then it explodes. Okay, and this sends out this specific light that gets really bright, and then it dies off over a couple of days, and it's a very clear-cut spectrum of light that it emits. We also know that they all seem to have exactly the same brilliance, and that's why we use them as standard candles, because if we know their apparent magnitude when we see one occur in a distant galaxy, we know that they all have the same absolute magnitude, and from that it allows us to work out the distance to that galaxy. But this is what we see. This picture here is what we see after a supernova has occurred. This is, I think, the Crab Nebula, which is basically all the stuff that's sort of just floating out in space. It's a nebula in its own right. It will eventually collapse. It could collapse eventually and then form another star. Okay, as you probably know, our sun is a second generation sun, so it's formed from, it's part of, the leftovers from a star that has gone supernova in the past. Okay, so as we've said, what's left after a supernova explosion basically defines what it is. Sorry, what's left after a supernova is defined by its mass. Okay, so if it is now this magic number 1.4 solar masses, this is the Chandrasekhar limit, more than that in a minute, but if it's less than the 1.4 times this mass of the sun, it's going to be a white dwarf. If it's between 1.4 and 3 solar masses, then it'll be a neutron star, and if it's more than 3 solar masses, then it's a black hole. Now this is only the mass of the core. The star itself could be a lot more than this. It's what's left over afterwards. What happens to this super dense core that's left over after explosions. So let's take a little look at these things and sort of find out what they really are. So with these neutron stars, the first thing that happens is the pressure, the weight, the force, if you will, of the core crushing down itself is sufficient to overcome the electron degeneracy pressure. That basically means that the electrons are forced onto the protons and form neutrons. But if it's over and this happens if it's over 1.4 solar masses. Unless it's more than 3 solar masses, though, that's as far as it can go. It can only go down as far as these neutrons, and then that is that. So they are very small. They're very dense. I mean, humongously dense. 4 times 10 to the 17 kilograms per meter square. And if you compare that to, say, terrestrial matter, if you think about something like lead, which is 11 tons per cubic meter, so that would be 1.1 times 10 to the 4 kilograms per meter cubed. Okay, so that'd be 1 times 10 to the 4. This is 10 to the 17. It is literally millions of times more dense than lead. Okay, so that means that the core is very small, 20 kilometers diameter, pretty small, you know, like a small moon, and they tend to spin fast because they have stars were spinning when they're big. It's a conservation of angular momentum thing, but basically they tend to spin very, very quickly indeed. And as they spin, a lot of them, okay, produce these beams of radio waves which are coming out from not the opposite angle, the opposite ends to the axis of rotation. So they rotate along an axis. If you look on this picture here, you see there's an axis of rotation at 90 degrees to that. Basically, there's like this beam of radio waves that are being sent out, and they're spinning very fast, you know, so up to 600 hertz. Most of them are less than 600 hertz, but up to 600 hertz. And these are known as pulsars. Okay, so they're very high frequency radio signals coming from stars, from dense neutron stars that are spinning far away in space, and they're quite fascinating things to study for scientists, because for a while they were thought to be potentially, you know, terrestrial communication from you know, aliens or something. So that's one of neutron stars, over 1.4 solar masses, under 3 solar masses. So what happens? What is these black holes? As we've said, if the core is over 1.4 solar masses, then it's able to crush the electrons to form neutrons. We're going to get this neutron star. But if it's over 3 solar masses, then it's a completely different situation altogether. Basically, the force is so great, okay, that it overcomes the strong nuclear force, and the whole core contracts and just crushes down into a super dense and infinitely dense point called a singularity. Now, people like to talk about big black holes and small black holes. As far as we are aware, there is no actual volume to a black hole at all. It doesn't take up any space. It's a completely super dense point. But what we can talk about is the event horizon, which is basically given by this idea of the Schwarzschild Radius. Okay, so we'll come to the Schwarzschild Radius in a minute and sort of talk about what's going on there. But black holes represent the deaths of stars. They can swallow up everything that comes into their path. What tends to happen, luckily, generally, is that things tend to orbit them because they are massive and therefore they have a huge force, and so we tend to get things orbiting them. But they can, of course, just suck in all the matter from a star, no problem at all. Okie dokie. So let's just have a little recap. We talk about supernova. It's this rapid increase in absolute magnitude. It's an exploding star. The ones that we're really interested in are the type 1a supernovas, okay, and remember they have strong silicon absorption lines and have a very clear cut, very peak to a high luminosity, and then die off over a very steady pattern of getting dimmer. Neutron stars are made of neutrons, and black holes are the singularities that will be that not even light can escape from. So obviously, if we're looking at the relative sizes, well, the sun, of course, is that yellow thing on the side. A white dwarf is, you know, a white dwarf is in the order of, you know, typically the size of a sort of planet, you know, about the size of the Earth. But you can see that by comparison, the neutron star is so much smaller, because it's been crushed. All that mass has basically been crushed down into a neutron. Now a black hole is basically even smaller. We don't know how big a black hole is, but it's a singularity. It's almost considered to be a point. So that's they get a lot smaller. Now how can we see these black holes? Well, basically the answer is we can't actually see them themselves, but what we can see is the emissions of gamma radiation when things fall into them. Okay, so as matter falls into a black hole and accelerates towards the speed of light, we get these bursts of gamma rays. Okay, and we get these bursts of gamma rays that we can see, which we can detect from Earth. Now, typically, when they are very, very short-lived and less than a second, we believe they are caused by neutron stars falling into black holes. When they last between 10 and 1,000 seconds, we believe them to be we know them to be the gamma radiation emitted when a star goes supernova. Okay, so we can see them in that way. We can also see black holes through what we call gravitational lensing, where light is bent as it goes around or near to a black hole. And we can also see that often we can see stars orbiting a black hole. So just by looking at the movement of things we can see, we can detect where there are objects of mass. But you can't see a black hole. It's not like a black thing that you can see in space. So that's what I just said there. That's that. Okay, so now we're going to look at the event horizon and the Schwarzschild Radius. Basically, the event horizon is the region, the horizon at which there can be a detectable event, i.e. it's the horizon of the area around the black hole where anything that emits some sort of information at the speed of light, okay, can be detected. If that event horizon is at the Schwarzschild Radius, the Schwarzschild Radius is the distance from the black hole itself, from the centre of the black hole to the event horizon. Okay, and we're going to look at really what this means and how it works in right now, basically. So, if we go back to gravitational, our study of gravitation, we know that we can work out the potential energy, the gravitational potential energy of an object using the equation GPE, is G_mm/r. It's negative, of course. We remember that because gravitational potential energy is always negative. We know that the kinetic energy of any object is a half mv². Now, if we wanted to accelerate, if we say we wanted to shoot something straight up into the sky so that the kinetic energy as it left the surface was sufficient to overcome the to completely give us enough gravitational potential energy to take it from that negative value on the surface all the way up to infinity where it's zero, then at that stage those two would be equal to each other. And so we can see this bottom equation here, half mv² would be equal to G_mm/r. So using that, if we just rearrange to make v the subject, obviously we've got m on both sides of the equation, that will go out of it, and you can see fairly quickly that will become, v will be equal to 2Gm/r, and then we'll have to square root all of that. So we get to this stage here fairly quickly. Now, the boundary of the event horizon, as we said, is where nothing can happen. And if we set the escape velocity to the speed of light and make that v for, replace the v for the speed of light, then of course these are all constants. Okay, well, for any given, this is constant, this is constant, therefore for any given mass of a black hole there will be a Schwarzschild radius, okay, which is the radius of the event horizon. Okay, so we can therefore rearrange it to make this, put it into this context, into this formula, and this allows us to if you know the mass of a black hole, it allows you to work out the Schwarzschild radius for it. So it might be a good idea to stop this now and maybe work out what would be the event horizon, or the Schwarzschild radius, sorry, for a black hole. Let's say a black hole of 2 solar masses. Okay, so calculate that for a black hole of 2 solar masses. Obviously, one solar mass, a solar mass is 2 times 10 to the 30 kilograms. So 2 solar masses would be 4 times 10 to the 30 kilograms. You stop the video now, and we'll go back through that in a sec. So hopefully you could have found that to be around about just under 6,000 meters. Bear in mind, of course, this would be the distance from the center of the black hole within which no light could escape. Okay, it's simply it would not be able to overcome the gravitational field strength within that distance. This is not to say the black hole is this size, but you just can't say anything more than we can't say what's going on within this radius. Okay, but therefore we can kind of consider this to be the sort of external boundaries of the black hole, but it's not that's where the black hole starts and finishes. Not that within that there's matter and outside there's not. The black hole we believe to be a singularity, but obviously that's a radius that we can use regardless, to sort of say, well, nothing can happen be within that we can detect. Okay, so hopefully that makes sense. Let's take a look at the next bit of this. So really we could come up with a situation now where we want to work out the density of a black hole. If this is the case, then of course we'd be able to simply divide the mass now by the volume, so we can substitute this equation. We can use that, we can substitute this lot here, 2gm over c squared, in for r at that point, and therefore we can derive an equation for the black hole. And again, you can do that if you want to pause the video. If you don't want to, then it was here. So see if you want to work out the density for a black hole of 10 solar masses, and I will catch you now. So here we are. If we do run the numbers, it comes out, as you can see, to around about 10 to the 17 kilograms per meter cubed, which is, of course, you may remember the very similar density as nuclear density. Okay, it's in the same ballpark. But as a final note, please remember that is not the density of a black hole. The density of a black hole we think to be infinite. It's a singularity. It's infinitely high.